Welcome back to Very Ordinary Differential Equations. In this lecture, we begin studying second-order linear equations with constant coefficients, but that are not homogeneous, and we begin with polynomial forcing functions. We need to begin by introducing a little bit of terminology. Suppose we just have a normal second-order linear differential equation, y double prime plus p of xy prime plus q of xy equals f of x. If the forcing function f of x is not constantly zero, well then we're in a non-homogeneous situation. However, there's an associated homogeneous equation where I simply pretend the forcing function is zero. And this is called the complementary equation to the original. So whatever your second order linear differential equation is, if you change the forcing function to be zero and make it homogeneous, that's called the complementary equation. Now we already know that if you can find two linearly independent solutions, y1 and y2, to the complementary equation, which is homogeneous, then any solution to the complementary equation can be written as some linear combination of y1 and y2. But what about the original non-homogeneous equation where the forcing function might not be zero? Let's just pretend we can find a single solution y sub p for particular solution. So suppose we have all of the following. We've got our original differential equation, which is presumably not homogeneous. And y sub p is one particular solution that we managed to find. We also suppose that y1 and y2 are a fundamental set of solutions to the complementary equation, which is homogeneous. Then two things hold. Any function, which is a linear combination of y1 and y2 plus the single y sub p that we managed to find, will also be a solution. And conversely, any solution which could be found must be of that form. In other words, having found a single solution to the inhomogeneous equation, and a fundamental set of solutions to the homogeneous one, all possible solutions are given by the particular solution we found plus all possible solutions to the associated complementary equation. So again, what is the overall process? We want to find all possible solutions to a non-homogeneous equation, y double prime plus p of xy prime plus q of xy equals f of x. Do the following steps. Find a fundamental set of solutions to the complementary equation, the one where you set the forcing function to be zero. Also, find just one solution to the original non-homogeneous equation. And then all possible solutions are given by the one particular function you found plus linear combinations of the solutions to the complementary equation. In other words, compared to all of the work we've already done, the only thing that's new is finding a single solution to the non-homogeneous equation. Otherwise, most of the work is in finding a fundamental set of solutions to the complementary equation. The technique to find a single particular solution depends very much on the type of forcing function f of x. The first situation we're going to examine is where the forcing function is a polynomial and the coefficients are constants. So we have a y double prime plus by prime plus cy equals f of x, where f of x is a polynomial. So here's the problem we have cornered ourselves into. Can we find one particular solution, y sub p, to this second order linear differential equation with constant coefficients and a forcing function f of x, which we are now presuming to be a polynomial? Now, of course, if the particular solution we find happens to be a polynomial of degree n, well, its derivative will be a polynomial of 1 less degree, and its second derivative a polynomial of 2 less degree. Of course, we don't end up with negative degree polynomials here. If I take sufficiently many derivatives of a polynomial, I just get 0. I don't get negative degrees, but sweep that under the rug. So if y sub p happens to be a degree n polynomial, then so is a yp double prime plus byp prime plus cyp, because here we get a polynomial of lower degree, a polynomial of lower degree, and the original polynomial. So overall, this will be a polynomial of the same degree that y sub p is. Now, if we want this to produce a polynomial of degree n, because we have a polynomial forcing function f of x, all we have to do is assume, hey, why don't we assume yp is also a polynomial of degree n and see if we can solve for it. So let's take that idea and put it into practice. Can we find a single solution to 3y double prime plus 2y prime plus 4y equals x squared plus 1? The forcing function is a polynomial of degree 2, x squared plus 1. So let's assume that the particular solution yp is also a polynomial of degree 2. But a polynomial of degree 2 can have three terms, something times x squared, something times x, and then a constant. And I don't know what those are yet. However, the first and second derivative are very easy to compute. The first derivative is 2ax plus b, and the second derivative is just 2a. So if I take this polynomial, its first and second derivatives, and I plug it into the left here, I will try to then set it equal to x squared plus 1 in order to solve for a, b, and c. So 3 times the second derivative plus 2 times the first derivative plus 4 times the original function should equal x squared plus 1. On the left, we've got a bunch of different terms, and I'm going to collect them according to the power of x. How many x squareds do we have? The only x squared we get is here from 4a of them. How many x's? 4ax and 4bx. How many constants? 6a, 2b, 4c. And if these two polynomials are equal to each other, 4ax squared plus 4a plus 4bx plus 6a plus 2b plus 4c is equal to x squared plus 1, well then the coefficients of x squared should be equal, the coefficients of x should be equal, and the constant should be equal. So we end up saying that 4a, the coefficient of x squared on the left, must equal 1, the coefficient of x squared on the right. 4a plus 4b, the coefficient of x on the left, must equal 0, the coefficient of x on the right, and 6a plus 2b plus 4c, the constant on the left, must equal 1, the constant on the right. So overall, we assumed that our particular solution was a second-degree polynomial, ax squared plus bx plus c, and we now have various equations about those constants a, b, and c. Well, the first one directly tells me that a is a quarter. Once I know that a is a quarter, I can use that in the second equation to get that b must be negative a quarter. And now that I know the values of a and b, I can use the third equation to solve for c and get that it must be 0. So our solution, ax squared plus bx plus c, must have a is a quarter, b is negative a quarter, and c is 0. So the one particular solution must be 1/4 x squared minus 1/4 x. Second example, let's find all solutions to y double prime minus 2y prime plus 2y equals 6x plus 1. The complementary equation is given by y double prime minus 2y prime plus 2y equals 0. Because in this problem we are finding all solutions, not just one, we do need to solve the complementary equation as well. This gives rise to its own complementary equation, and again it is somewhat duplicate terminology, r squared minus 2r plus 2 equals 0. This has complex solutions 1 plus or minus I. So a fundamental set of solutions to the complementary homogeneous equation is given by e to the x cos x and e to the x sin x. Now we can turn our attention to finding one particular solution to the original non-homogeneous equation. Now the right, the forcing function, is a polynomial of degree 1, so let's assume that y also is some constant times x plus some constant. Its first derivative would just be a, its second derivative would just be 0. We throw that into the original differential equation, and we just get 0 minus 2a plus 2 times ax plus b must be the forcing function, 6x plus 1. We collect like powers of x and compare coefficients. So how many x's do we have on the left? 2a of them. How many x's do we have on the right? 6. So 2a must equal 6. What's our constant on the left? 2b minus 2a. What's the constant on the right? 1. So 2b minus 2a should equal 1. I directly get a is 3, and once we know a is 3, we can solve for b is 7/2. Therefore, the particular solution is 3x plus 7/2. So we have found one particular solution, 3x plus 7/2, and we also found a fundamental set of solutions to the complementary equation, e to the x cos x, e to the x sin x. Therefore, all possible solutions are given by one particular solution plus linear combinations of our fundamental set of solutions. So all solutions must be of the form 3x plus 7/2 plus some constant e to the x cos x plus some constant e to the x sin x. As a third example, let's solve an initial value problem. Y double prime minus 8y prime plus 16y equals 8x cubed, with the initial values y of 0 is 2 and y prime of 0 is 0. Well, first let's find all possible solutions and then we can worry about the initial values later. The complementary equation is given by y double prime minus 8y prime plus 16y equals 0. That has its own complementary equation, r squared minus 8r plus 16 equals 0. This has a single real root. It factors as r minus 4 squared. So a fundamental set of solutions to the homogeneous complementary equation is given by e to the 4x and x e to the 4x. Now we can try to solve for one particular solution to the original non-homogeneous equation. Now the forcing function is of degree 3, 8x cubed. So we assume that our particular solution is also a polynomial of degree 3, which must be something times x cubed plus something x squared plus something times x plus some constant term. So we've assumed that a particular solution is given by a generic cubic polynomial. We can compute derivatives of this pretty easily. Here's the first and second derivative. Now I take the original, the first derivative, the second derivative, and I throw it into the original differential equation. Y double prime minus 8y prime plus 16y is supposed to be equal to 8x cubed. Now we just have to compare how many x cubes do we have on each side, how many x squareds, and so forth. So let's first ask how many x cubes. On the left, my only x cubed is 16a x cubed, but on the right I have 8x cubed. So that tells me a must equal 1/2. Next, how many x squareds? On the left we have negative 24 times ax squared. That comes from this term right here. However, we also get 16b x squareds, but on the right we don't have any of them. So negative 24a plus 16b must equal 0. Now, having already solved that a must be equal to 1/2, negative 24a is just negative 12, and this allows me to solve that b must equal 3/4. Next, let's move on to how many x's. Well, on the left we have 6ax, we have negative 16bx, and we have positive 16cx, but on the right we don't have any. So we conclude 6a minus 16b plus 16c must equal 0. Having already solved for a and b, I can solve for 6a and negative 16b. With these numbers now being specified, we can solve that c must be negative 9 over 16. And finally, by looking at our constants, we get 2b minus 8c plus 16d must be the constant term on the right, which is 0. But since we have already solved for b and c, we can solve that d must be negative 3/8. So we assumed that a particular solution was a generic cubic. We computed its first and second derivatives, threw it into the differential equation, and compared to the forcing function of 8x cubed, and determined that a must be 1/2, b must be 3/4, c is negative 9/16, and d is negative 3/8. In other words, our particular solution is x cubed over 2 plus 3x squared over 4 minus 9x over 16 minus 3/8. But a few slides back, we determined a fundamental set of solutions to the complementary equation. So now that we have a particular solution and a fundamental set of solutions to the complementary equation, we can state that all solutions must be of the form yp plus a linear combination of y1 and y2. In other words, x cubed over 2 plus 3x squared over 4 minus 9x over 16 minus 3/8 plus some constant e to the 4x plus some other constant x e to the 4x. Well, having found what all solutions must look like, now we can turn our attention to the initial values we were given. Well, its first derivative is 3x squared over 2 plus 3x over 2 minus 9/16 plus 4c1 e to the 4x plus 4c2 x plus 1 e to the 4x. Our initial conditions were that y of 0 is 2. So taking our first expression up here, setting this equal to 2 and plugging x equals 0, this vanishes, this vanishes, this vanishes, negative 3/8. This vanishes, and e to the 4 times 0 is just 1. So we pretty directly find a value for c1. But if I take y prime of 0 is 0, I set this equal to 0, vanishes, vanishes, constant, 4c1, 4c2 times 1. So now we have two expressions for c1 and c2. With those two expressions for c1 and c2, we can solve that c1 is 19 over 8 and c2 is negative 143 over 64. Having found one particular solution and having solved for the coefficients c1 and c2 to use in our linear combination of our fundamental set of solutions, we now know the unique solution to our problem is given by that particular solution plus those particular constants for our fundamental set of solutions. X cubed over 2 plus 3x squared over 4 minus 9x over 16 minus 3/8 plus 19/8 e to the 4x minus 143 over 64 x e to the 4x. Overall, what have we covered? Finding all solutions to a non-homogeneous differential equation really just reduces down to finding one particular solution. We normally denote it as y sub p. Then you also have to find a fundamental set of solutions to the complementary homogeneous equation. In the specific setting where the differential equation has constant coefficients and the forcing function is a polynomial, we can assume that y sub p, the one particular solution, is also a polynomial and of the same degree as the forcing function. Then you compute all necessary derivatives, you throw it into the differential equations, and you compare to the forcing function. This will allow you to solve for the unknown coefficients in the particular solution yp.